Welcome back. Last time we proved this theorem which says that if you have a quintic polynomial over a subfield of complex numbers whose Galois group is either S5 or A5, then it is not solvable. Okay, so it gives us a way to construct a non-solvable quintic polynomial. We need to now go ahead and construct a polynomial whose Galois group is S5 or A5. So this previous class completed the course. Really, we have covered everything that we wanted to do. Remember, in the beginning I said the goal is to prove Galois theorem about solvability of polynomials with rational coefficients. We have done that. So I have some loose ends to take care of and also give some exercises. So the remaining few videos in the course will be exercises, and in this exercise sessions we will prove some results that we have used earlier in the course without proof, and I also will give you several examples on how to compute Galois groups and solve some interesting problems on Galois groups. Okay, so I am going to go ahead and start these, and one by one we will do, and we will see how much we can do. In the first problem, we will take care of the pending issue, which is construction of a polynomial with rational coefficient whose Galois group is S5. Okay, so in fact we are going to do a slightly more general problem as follows. So let P be a prime number and let us assume P is at least 5. Suppose F is an irreducible polynomial of degree P such that F has exactly 2 non-real roots. Okay, so it has P roots, of course, because it is a irreducible polynomial of degree P, it will have P distinct roots in complex numbers. I am assuming that it has exactly 2 non-real roots, other P minus 2 are inside R. Then Galois group of F is SP. Okay, so Galois group over Q, of course. Every time you take a polynomial in a particular field, a Galois group, when I refer to the Galois group of that polynomial, I mean the Galois group over that field. Okay, so remember, if you take P equal to 5, gives us a non-solvable quintic. Okay, so we have to, of course, construct a polynomial which has exactly 2 real roots. We will do that. So let us prove this. This proof is quite simple and it is instructive. So let us call the roots alpha 1, alpha 2, alpha 3, alpha p, b, roots of we can take k, f in a splitting field k, okay, of f over q, the usual sentence, right. So we have the splitting field of that polynomial. It will have p roots. Take call them alpha 1 through alpha p, and let us say alpha 1, alpha 2 are not in R. So alpha 3 and up to alpha p are all in R. Okay, we know that exactly 2 are not real numbers. So we have this. First, I claim that. Okay, so let G be the Galois group of the splitting field, which of course is what we call the Galois group of the polynomial. First, I claim that the permutation 1, 2, the 2 cycle 1, 2 is in G. Why is this? Consider the map from K to K given by complex conjugation, right. So here basically any A plus IB will go to A minus IB. Okay, so some general facts which one can show. Facts: sigma is an automorphism of K, and which of course fixes Q. Any automorphism of an extension of Q fixes Q. So it is an element of the Galois group, and also sigma of alpha 1 is alpha 2, sigma of alpha 2 is alpha 1, and sigma of alpha I equals alpha I for all I from 3 to P. Yeah, these are some general facts, right? Because we know that roots of a rational polynomial, complex roots of a rational polynomial appear in conjugate pairs, non-real complex roots. Okay, so alpha 1 and alpha 2 are basically conjugates of each other. Everything is a conjugate. I mean, if of course alpha 3 is also a conjugate of itself, but that's because conjugate of alpha 3 is alpha 3 itself, because they are real numbers. But otherwise, the non-real ones appear in conjugate pair. So this is an easy exercise. Okay, I'm going to, in order to do as many problems as I can, I'm going to skip some facts which are either group theoretic or some general facts that come from earlier parts of algebra, so that I can focus on the Galois theory part. So this is one such. So we assume these facts. So sigma is in fact, right? So sigma is in fact the permutation 1 2, because it sends 1 to 2, 2 to 1, and it fixes all others. So 1 2 belongs to G, right? So sigma is in G. So this is in T. So G contains a 2 cycle. So G contains a transposition or a 2 cycle. Now next I am going to argue that it also contains a P cycle. So we have because F is irreducible, the action of G on the roots is transitive. So there is an order of orbit of order P, size P, so P divides it, or more directly we have K containing Q alpha 1 containing Q, and this is a degree P extension because F is irreducible, right? That is because the irreducible polynomial of alpha 1 is F. So this is a degree P extension. Hence P divides K colon Q, which is of course the order of G. But by Cauchy's theorem, G contains an element of order P. Okay, this so far we have not used the fact that P is prime, but now we are going to use. So P prime implies G contains a P cycle. Okay, this is only true for prime P. In general, if you have an order 4 element, it doesn't mean it's a 4 cycle. However, for P prime, it must mean. Okay, this requires some group theoretic facts. Okay, so I'll just order of a product of disjoint cycles, okay, is equal to LCM of order of each of those individually. Okay, so now in order for a element to have order P, that element can be written as a product of disjoint cycles, and those orders will have LCM P, but they are all, because P is prime, this implies this. And as I said, I am going to leave certain group theoretic statements as exercises for you. So any element of order prime must be a P cycle. It cannot be written as a product of cycles of different sizes. In general, you can do that, but not if P is prime. So G contains a P cycle and G contains a 2 cycle. So now again a general fact, which I will in fact quickly prove because this is an important fact. So if G in Sn contains, here n is any number, a 2 cycle and an n cycle, then G is Sn. So any subgroup that contains a 2 cycle and an n cycle is all of Sn. So the fact proof of this is we can assume 1, 2 is in G. Let's call that sigma. Of course, the way that is just a matter of rearranging the indices, but we can also assume that this is the n cycle, because you take an n cycle and you take some sufficiently, powers of them one by one, eventually you will get this, because n cycles form a cyclic group and they're all powers of each other. Okay, so any n cycle you have, you can take some power and you can get this particular n cycle. Okay, let's call this tau. So then it's an easy computation. Tau sigma tau inverse is actually 2, 3. This is because you can work this out. This is a trivial exercise. So just write down tau inverse, then apply sigma, then apply tau, you get this. So now that means this is in G, because tau and sigma are in G. Any product of things in G is in G. So that is in G. But if you do tau times 2, 3 times tau inverse, that is actually 3, 4. That's in G. So this is also an exercise. So I'm not doing the explicit computation here, because that's easy and you can do this. So similarly, we can conclude that I plus 1 is in G for all I. So we have 1, 2 by hypothesis, 2, 3 I have exhibited, 3, 4, and then you do tau 3, 4, tau inverse, you get 4, 5 and so on. But once you have these, you can now compute 1 I is actually equal to 1 I minus 1 I minus 1 I 1 I minus 1. Okay, so this is in G by induction, this is in G by this construction, this is in G of course by induction. So this whole thing is in G. So that means I am going over this very fast, but 1 comma I is in G for all I. Now it's well known that they generate Sn, in particular because you know that 1 comma I times 1 comma j times 1 comma I is actually I comma j. So 1 goes to I goes to 1. So I goes to 1 goes to I goes to 1. So 1 is fixed. I goes to j goes to 1, 1 goes to I. So j goes to I, and similarly I goes to j. So that means all this very quickly what I have said is G contains all 2 cycles. But then it is well known that every permutation Sn is a product of 2 cycles. Okay, so this is a standard group theory fact, but I sort of try to give you a quick proof of this. Okay, so I hope I didn't confuse you. You can just note down all the equalities I wrote here and just check them one by one. It's a trivial check. So if a group contains Sn, if a subgroup of Sn contains a 2 cycle and an n cycle, it is Sn. So now our Galois group here contains 1 to end a p cycle. So applying this to our situation, this is as required, right? So the problem asks you to show that if you have an irreducible polynomial of degree p which has exactly 2 non-real roots, the conceptual part of it is very simple. The complex conjugation permutes the non-real roots, fixes all the real roots. So that's a 2 cycle, and because you have an irreducible polynomial, you have an order p element. Because p is prime, it must be a p cycle, and a general fact about symmetric groups is that any 2 cycle comma any p cycle together will generate all of Sn. So G is Sp. Okay, this now settles the question of polynomials having Galois group Sp. Now we have to still construct a polynomial with exactly 2 non-real roots. Examples of polynomials, of irreducible polynomials with exactly 2 real roots. Okay, so I am going to give you a couple of them to completely settle the issue. So what we do here is, so this is, let me just go and quickly tell you this. So the point is, we need for degree 5 first, okay, because ultimately the whole point of the course is produce a quintic which is not solvable. So what I want is exactly 3 real roots. So let's take the polynomial x power 5 minus 4x. Okay, let's take this polynomial. Of course, this is not irreducible, but what kind of polynomial is this? We have x times x power 4 minus 4. Okay, so this is actually, let me take, yeah, so this is x times x power x square minus 2 x square plus 2. Okay, so this degree 5 polynomial has exactly 3 real roots. So then G has exactly 3 real roots, exactly 3 real roots and 2 non-real roots, right? So the 3 real roots are 0, square root of 2 minus square root of 2 and okay, so the non-real roots are root 2i minus root 2i. Okay, so these are not in R, these are in R. Now this is a good polynomial for us, except that it is not irreducible. So if you look at its graph, it looks something like this, right? So it goes through 0. So this is 0, this is square root 2, this is minus square root 2. Okay, this is the graph of G. But now what I do is shift this up by, let's say 2. So let's say fx equals gx plus 2. So this is x power 5 minus 4x plus 2, and this is irreducible by Eisenstein. So I have chosen 2 so that you get an irreducible polynomial. What is the graph of this? I claim that its graph is basically shifting this up by 2. Okay, so graph of okay, so this is the graph of okay. So you can also use some calculus to intermediate value theorem and mean value theorem to give a concrete proof, but it doesn't matter. So it's clear that when you shift this, it will continue to have 2 real roots, 3 real roots. So we conclude f has exactly 3 real, 2 non-real roots. Okay, so this is a function, polynomial, irreducible. It has 3 real roots and 2 non-real roots. Okay, so one has to do a little bit more work. Check this carefully. Okay, so I will leave that part to you, because that is just, you can compute, for example, that it will be negative here, positive here, so it will at least cross x-axis 3 times. It cannot cross more than 3 times because G does not. Okay, so hence Galois group of F is S5 and F is not solvable. Yeah, so this is good. So this means that you have a polynomial of degree 5 which cannot be solved by radicals. So this is the main result of Galois theory in some sense. Okay, so Galois gave an explicit construction of polynomials which cannot be solved by radicals. So I'll give you one more example which is along the same lines, but I thought it would be good to have one more example. So this is irreducible by Eisenstein. and this can be written as x times x power 4 minus 4 minus 16 plus 2. So, this is x times x square minus 4 x square plus 4 plus 2. So, this has exactly 3 real, 0, 2, minus 2 and 2 non-real roots, and hence so does f. So, again it is irreducible, it has exactly 3 real roots, Galois f is S5. Okay. So, this proves that this is also not solvable. You can in fact construct now any for any n, let fx be x power n minus 5 times, let us say, x power 5 minus 6x plus 2. Okay. So, then Galois group of f, of course, f is not irreducible. But however, we know that Galois group of f is S5, because this already has roots. So, splitting field of f is the splitting field of this, which is S5. So, this implies f is not solvable. Every time you have the Galois group S5 or A5, it is not solvable. So, hence for every n we have a polynomial of degree n which is not solvable. Of course, we do not have a irreducible polynomial, that requires a significantly more work, but for prime numbers we can construct that. So, let p greater than or equal to 5 be a prime number. Let f be x power let us say x square plus 4 times x minus 2, x minus 4, x minus 2 times p minus 2 plus 2. So, this is of course in Qx. Degree f is p, because these are p minus 2 terms here, there is a square term here. So, degree is p. So, I claim that f is irreducible. Okay. So, the proof simply uses Eisenstein criterion, because if you now expand out, f can be written as x power p plus these are all even numbers, right, 4, 2, 4, 2 times p minus 2. So, every term that you have in the middle of this polynomial, all intermediate terms like this, are even. Okay. So, you can factor out a 2, right, because if, for example, what is x power p minus 1 term. So, you have to take degree 2 and all but one of these. So, you have to take p minus 3 of these, right. So, and the last one you have to take the coefficient. So, that is even. So, that will be even times x power p minus 1. Okay. So, and then what is the constant term? Constant term is 4 times. So, you will have actually here, so 1, 2 up to p minus 2 terms. So, you have to take these minus 2, minus 4, minus 2 times p minus 2. P is odd, so p minus 2 is odd. So, there will be a minus sign here. And then you will have, so I will write the constant term here, minus 4 times 2 times 4 times 2 times p minus 2 plus 2. Okay. But this is divisible by 4, obviously. So, the constant term is even but not divisible by 2, by 4. Because 4 divides this term and 4 does not divide this. So, constant term is even but not divisible by 2. So, you can apply Eisenstein to conclude that f is irreducible. So far so good. And now I claim that f has exactly p minus 2 real roots, right? And this is the reasoning is same as above. What is the reasoning? Reasoning is you look at g, which is x power p, so f is g plus 2, okay. So I am taking this to be g, yeah, so I am taking this to be g. Then g has roots plus or minus square root of minus 4 and 2, 4 up to 2 times p minus 2. So this is not real, these are real, okay. So and then you shift up by 2. So that means f will also have exactly 2 non-real roots and p minus 2 real roots. So f has exactly, f is irreducible, has exactly p minus 2 real roots, and hence, okay. So in particular, so I want to highlight this because we will get back to this later. In particular, we constructed a Galois extension k over q such that Galois k over q is isomorphic to SP for any prime, right, for any prime p at least 5. So I want to come back to this statement later, because the question is given any group, can you construct such a Galois extension? That is an open problem, very famous open problem. But so what we have really done here is that we can do SP. This example won't give Sn because this is not an irreducible polynomial, it only gives us S5. Okay, so this settles the question of exhibiting polynomials which are not solvable by radicals. Okay, now what I want to do is do some examples of computing Galois groups. So this might be a good time to stop. So let me stop this class here, and in the next class we will continue with more exercises. Thank you.